Hey kids, new unit time. So we're going to be looking at exponential functions in this unit. We're going to start with geometric sequences and series, and then lead into the exponential stuff. Let's have a look. So our first section here, 4.1, geometric sequences. We're going to start by just defining what this simple concept is. A geometric sequence is a list of numbers where each successive term is multiplied by some common ratio r. So it's a really simple idea. You start with a number like the number 2 and you multiply it by some number. In this case, you're multiplying it by 2, then you're multiplying 4 by 2, and you're multiplying 16 by 2. If you keep multiplying it by the same number consistently, then it's geometric, and we would say r is equal to 2. You can start with the number 9 and multiply it by negative a third so that the signs keep alternating. And you could also try and do this, but this is not geometric, because if you notice here, you can't multiply 3 by something to get 5 and then multiply 5 by that same thing to get 7. In fact, what we have here is we have an adding sequence rather than a multiplying sequence. So this is not geometric. It is actually called arithmetic. We're not going to learn about that. They're fairly simple, and they're not really going to lend themselves too well to what we do in this course, but just so you know, that's an arithmetic sequence. Okay, so these first two are geometric because we're constantly multiplying by the same thing. So example 1, which of the following sequences are geometric? This is really similar to what's above. You can see that every time we're adding 2. You might be going, well, could we be multiplying by 3? But you're not multiplying by 3 to get to the next thing. This would be what, like 5 over 3 or something like that. It's not going to work. So this is not geometric. Okay, you can only get to the next term by adding. Therefore, it's not geometric. Okay, this one though here is you can actually see that going from 1 to 10 to 100 to 1,000, every time we're multiplying by 10. You're not adding a number every time. You're multiplying by 10 constantly, so therefore it's geometric. Part C, the length of the lines in each row. This is actually called the Cantor Set. Some guy named Cantor came up with this. Very simple idea, but it's really pretty. This actually explains why they're called geometric. This is a geometric progression because as you start at 1 and the third and the 9th and 1 over 27, you can see every time we're multiplying by a third, the third, and so on. This makes a geometric shape. Geometric just means shapes. When you do geometry, it's like the math of shapes. So what we can see is this actually makes a very nice little elegant picture there. There's all sorts of geometric sequences that make shapes. You can even do something simple like have a box, and next to it stack a box half as tall, box half as tall as that, half as tall as that, half as tall as that, and so on. And you're actually going to get this nice little shape. The shape you wind up getting tends to have this nice little curve to it. And we can even draw a similar curve to this. You could say the ends of these lines, we drew a curve going through it. They wind up having a similar sort of shape. This, by the way, is what you would call an exponential curve. We're going to talk about exponential stuff a bit more. It's definitely super related to this, which is why it's in the same unit, but coming up at a later date. All right, here's a general formula that's going to be really helpful. This formula looks like it's something magical that people spent years and years to derive, and it's absolutely not. It's a total common sense formula. It basically looks like this. So if you want to know the nth term in a sequence, you start with the first term, you're going to multiply it by r, and you're going to do that n minus 1 times. And that's how you're going to calculate any term. So what this means, very simply, is let's say I know the first term, and the second term, the third term, the fourth term, and so on. If I want to figure out what the fifth term is, I don't need to know T2, T3, T4. All I need to know is that I'm multiplying by r every time. And I can actually shortcut this whole thing. If I want to know the fifth term, I don't have to write it all out like this. I can actually go straight from this. I don't need to know these guys. Let's get them over there. I can go straight from here to here if I want. How many times did I multiply by r to go from T1 to T5? 4 times. And we can see in general, if you know the first term and you multiply it by r, one time less than the number of terms you want. So if I want the fifth term, I have to multiply by r 4 times, then I'm going to be able to calculate it. So this formula is super common sense. It's just simply saying, let's take the first term, let's multiply it by something a bunch of times, and it just has to be one time less than whatever term I want. So in the Cantor set above, how long is each line in the 12th row? You could do this. You can say that, well, the first row is 1, the next row is 1/3, then a ninth, then 1 over 27, so on, right? 1 over 81, and then the numbers get hard. So what math's going to allow us to do here is it's going to allow us to not have to go through and calculate every single thing. We can shortcut it. So in this case, how long is each line in the 12th row? We would understand that to be T12 equals, I don't know. We know the first term, which is the length of the first line, is 1. We know r, which is how short the next one is as a multiple of the first. That's a third. N is equal to 12 because that's the number of lines, or the number of rows, I guess, and T12 is the question mark. It's really common for people to mix up N and Tn. So in this case, N is the number of terms. T12 is the value of the 12th term. So just don't get those confused. Okay, so finishing this all up here, T12, which is the length of the 12th line, would be T1 times r to the 12 minus 1. So the first line has a length of 1, r is a third, and we'd raise that to the power of 11. This is 1 over 3 to the power of 11, which I don't think I can do in my head, but a calculator can quickly help us out here, so I'm going to just use the terrible Windows calculator, and I'm going to calculate this 3 to the power of 11 and 177,147. Okay, so what we can tell is that if I was to actually work this all out and keep doing this repeated multiplying by a third over and over and over, and I did that 12 times, well, actually I'd only do it 11 times to get to the 12th row, but this is how long it would be. So that's a much better way of doing it than working it out. Okay, working it out the long way. Question 3. This is a nice little textbook style question. In a geometric sequence, the third term is 25 and the seventh term is 50. So this here is T3 and this here is T7. If we have to determine the common ratio R, if you haven't thought about this too much, you might want to pause the video and think about this. What is the way we're going to determine R? And it's not as simple as 50 divided by 25. Okay, now if you've given that a little bit of thought, or maybe you haven't, but let's write it out. I like to do these little pictures. Okay, so T3, we don't know T4, we don't know T5, we don't know T6, but we do know T7. If I'm going to go from here, this by the way has a value of 25. This guy has a value of 50. How are we getting from T3 to T7? We have to multiply by R 4 times. So if we want to figure out what R is, we have to realize that shortcutting from T3 to T7 is like multiplying by R to the power of 4. And what we can see here is 7 minus 3 is 4, and that's absolutely not a coincidence whatsoever. So the way we can work this out is we can think about this, first of all, we can think of this in terms of sort of a general statement. In general, R is T, let's say T2 over T1, which should be the same as T3 over T2 and so on, right? So if you take a term and you divide by the previous term, you should always get R. And if R isn't the same, then it's not geometric. Okay, so in general though, more generally, we can actually come up with another formula that says, if I know TB and I divide by TA, in this case, this would be like T7 over T3, R would be B minus A. That would be the exponent on that. So if I have two terms that are separated apart by more than 1, so like T7 and T3, I can work out this guy to say r to the power of 4. So in this very specific case, this would be r to the power of 4, would be T7 over T3. Okay, so what I can see here is T7 is 50, T3 is 25, and therefore I can conclude that r to the power of 4 is equal to 2, or r is equal to the 4th root of 2. Okay, so that's my common ratio right there. If I want to know the value of the first term, there's a few ways you can do this. One way is to just use some common sense here and say, if I know, let's change color here, if I know T3 is here, I can back up 2 spaces to get to T1. And what I should be able to do is if I'm going to the right, I'm multiplying by r. If I'm going to the left, I'm dividing by r. So a real common sense approach to this would be to say that T1 is equal to T3 and you divide it by r squared. So what I could do is I could say this is 25 and I'm going to divide by r squared. Now we're going to have to do a little bit of fractional exponents here to make sense of this. So this would be 25 over, let's see, this can be written as 2 to the power of 2 over 4, which can actually be written as 2 to the power of a half, which is actually just 25 over root 2. Some people will want to rationalize it, but you know what? I never liked rationalizing those denominators, so I'm going to leave it like that. Okay, so that's one approach you can do. So this is sort of like logic. Another approach, I'm going to call this the logical method. Another approach is using the formula. So what we can do is we can say that in general, T3 equals T1 to the power of r to the 3 minus 1. If I actually want to work using this formula, I can rearrange it to say that T1 equals T3 over r to the 3 minus 1, which is r squared, and that winds up giving the same result. So you can definitely just use the formula, or you can use common sense. So this is kind of the logical method here. This is the formula method, but you get the same result. Okay, so now if we're looking for the value of the 10th term, again, we're going to have something similar here. I'm going to switch to maybe green because I actually want to show how you can do this without doing any real serious formula work. T8, T9, T10. How many more times do you have to get or multiply by r to get to T10? And you're going to have to multiply by r cubed. So the way you could actually do this is you could say that in general, T10 would be T7 multiplied by r cubed. If you're a pattern noticing person, you might actually see something very curious here. 7 plus 3 is equal to 10. And you can actually kind of modify this formula way up here. This guy right here. You can say that 1 plus n minus 1 equals n. And as long as that's true, it's always going to work out. So you can change the subscripts and exponents to whatever you want. So this would actually be T7 was 50. R was the 4th root of 2, but we're going to cube it. So this is going to give me 50 to the power of, multiplied by 2 to the power of 3 over 4. And that's what it would wind up being. So if I want to actually work this out to have a number, just to double check my work, maybe I will. I'm just going to go over to my calculator. I have a few instances open. Because this is the terrible Windows calculator, I'm actually going to write it as 2 to the power of 3 divided by 4 in brackets, push equals, and then I'm going to multiply that by 50, and that tells me about 84.09 or something like that, right? So this would be about 84.09. You can just replace that with a squiggly equal sign because it's not perfect. The reason why I want to do this is I want to make sure this makes sense. Does it make sense that the 10th term would be about 84? So if I'm looking at this, if I got 25 here and I got 50 here, by the time I get to the end, 10th term, it should be 84. Well, at least it's bigger. That makes sense. Here's a little skill testing question. What would be the 11th term? I'll give you a hint. You don't need to use a formula. Think about it. Pause the video and actually think about it. Okay, so if you actually did that pausing, you would realize, hopefully, that 25 is T3. You move forward 4 spaces to get to T7, you're at 50. What happens if you move another 4 spaces to get to T11? That would actually have to be exactly 100. And if you work it out with a formula, I can guarantee you it's going to work. Okay, so having 84.09 actually seems reasonable. Hope we didn't make a mistake. Okay, here's our last question. I like this one because I think it's quite an interesting realization. If you're a band player, you play piano, you might realize this. If you're not, well, here's a fun little fact for you. The notes on a piano, you know, there's a piano, okay, it looks like this. Okay, let's all laugh at me drawing a piano, but okay, so we've got like black key, black key, black key, then we got a gap, and then black, and 3 blacks, and 2 blacks, and anyway, so the keys, the way they're spaced, there's 88 of these, black and white keys. And if you start here, and this key is an F, and you move up to the next key, the black key is F sharp. I always forget which side you're supposed to put it on. Let's just say it goes on that side. And then you move down here, then you got G. Every time you're moving up one note here, you're multiplying by the 12th root of 2. So as you're going from F to G, you're multiplying by, you've got 2 steps there, so you're multiplying by the 12th root of 2 squared, and so on. So if you start at the very lowest note on the piano, which is the lowest A note is at 27.5 hertz, I think I had to look that up, and there's 88 keys in total, what's the frequency of the very highest note? So somewhere over here, you're ending, you've got an A, that's the lowest A, this is 27.5 hertz. And all the way over here, all the way over here, you're going to end with a C, and that's C, and we want to know how many hertz is that. Okay, so you could sit there and you could say 27.5, and you can multiply it by the 12th root of 2. And you could do that like 88 times, but we're going to use geometric series to, or sequences, I should say, to help us out. Sometimes I say series instead of a sequence. If you're wondering what the difference is, there is a difference, and that's actually going to be the next lesson. Anyway, so the geometric sequence is this. The first term is 27.5 hertz. R is the 12th root of 2. In this case, what is N? Well, there are 88 keys, so we know the first key here is T1, which is 27.5, so N is 88 for 88 keys, because this is the 88th key over here. And then finally, we're interested in what is the value of T88. So if we want, we can figure out the frequency of the very highest note, and we can say that T88 is equal to T1 times R to the 88 minus 1. So we could say the first note has a frequency of 27.5 hertz. This is the 12th root of 2, which is a weird number, but don't worry about it. And then that's 87. So what we would actually be typing in on the calculator here is we would say, here's 27.5 multiplied by 2 to the power of 87 over 12. And even though this seems like a weird number, it's not a big deal. It's just whatever it is. Okay, so let's grab this guy here. Let's move over. So the way I'm going to type this in, again, I'm going to go 2 to the power of, I'm going to use brackets, 87 divided by 12, and what this should give me is 7.25, and then times 27.5. So if I do this, and I do this all right, apparently I should be hitting a note of about 4,186 hertz. Oh boy, okay, so 4,186 hertz approximately. Okay, so I think that seems reasonable. When you think about what kind of sounds you can hear if you've ever played a piano, hitting that very highest note is quite loud and quite high-pitched and unpleasant, and 4,000 hertz, well, the most a human can hear is about 20,000 hertz, even 15,000 for older people starting to get part to here. So this seems reasonable. One other thing just to think about here, again, this is really something that the people who do play instruments will understand. If you've never played an instrument before, you might sort of miss out on this, but I think it's worth mentioning. So the way I did this here is I've got an A here, and I've got there's another A here, and there's another A here. There's another A down here somewhere, right? And you keep going up by, this is what's known as an octave. To go from one octave to another, there's 12 steps. So one interesting thing just about how a piano is created, we could also think about what is R going across 12 steps? Because we know R going across one step is the 12th root of 2. So what is R going across 12 steps? Well, our 12 R's would be this to the power of 12, which is just 2. So one interesting little fact about pianos and a lot of musical instruments is every time you go up an octave, you're actually going up. To go from here to here, you're going up multiplying by 2. So if this low A is 27.5, the next one is going to be at, what is that, 55? And then the next one's going to be at 110, next one's going to be at 220, next one's going to be at 440, and so on. So they actually have this nice geometrical progression, even in spaced out quantities. You don't have to go from A to B. Oh, I realize this is actually drawn absolutely horrendously. Whoops. Okay, so anyway, yeah, okay. Well, I know some band kid is probably getting really upset at me here, and I just sort of did this without thinking. Sorry. Here is A. Okay, so let's erase that. Let's stick with that. Okay, so going from A to A, octave A is you're doubling every time. So you don't always have to go from A to B and say there's 12th root of 2. You can even take terms that are spaced out further than that and say they're geometric. And this connects with what I was saying up here, where T1, T2, T3, T4, they're all geometric with each other. But if you took T3, T7, T11, T15, and so on, that would actually be geometric. It would be its own sort of geometric progression. So it's kind of a neat little thing there. Anyway, that's it for this.